Here we are on page 2 of the stoichiometry practice test for chemistry 1. So, again, I want to double check my equations. How many molecules of water will be required to react with 32.9 grams of lithium nitride? Oh boy, a few typos on the sheet. According to the following reaction, I want to check if my equation is balanced. 3 lithiums here, right? For each formula unit of lithium nitride, I have 3 lithium atoms. 3 lithium atoms, 3 lithium atoms. 1 nitrogen, 1 nitrogen. 6 hydrogens. Because each H2O has 2 oxygen atoms, I have 3 of them. That means I have 3 here, that's 6. And then 3 oxygens, which I have there. We're good. Balanced reaction. So, after that, I want to anchor myself. I want to know what I'm looking for. What do I know? What am I given? I'm giving 32.9 grams of lithium nitride. I'm going to ask how many molecules of water. But first thing, I have some units. I'm going to turn those units into moles. So, I need to find the gram molar mass for lithium nitride. Lithium's about 6.9, so 6.9 times 3 is 20.7, plus 14 for nitrogen, 34.7 grams is my gram molar mass for lithium oxide. So my grams cancel out. I have 32.9 divided by 34.7 is 0.948. Since I'm working with 3 units here, I'll do 0.948 moles of lithium nitride. All right. From there, I have 2 possible routes of action. I did my balanced equation, I did my units to moles. Now I can either cross multiply or I can just cancel out units. What I'm looking for, what my interest is water. So I can set up a cross multiplication where I have 1 mole, well, let me write it as a mole. 1 mole of lithium nitride over, in this case I would be requiring 3 moles of water, would equal my moles of lithium nitride, which I know, over the moles of water, which I don't know. Now I have to expect it's going to be something close to 3. This number is something close to 1. My moles of water is going to be something close to 3 because it's a 1 to 3 ratio. For every 1 mole of lithium nitride, I need 3 moles of water. So I actually would get X equals 3 times 0.948, which would equal 2.84 moles of, I was solving for water. Now again, remember that's not the only way I can go about this. I can do it a different way. I can multiply this with my mole ratio. So it would be times 3 moles of water over 1 mole of lithium. Lithium. I think I need a new pencil. This one's dead. All right. 1 mole of lithium 3 nitride. So now my moles of lithium 3 nitride cancel out. I'm left with moles of water. And surprise, surprise, I get the same number. 2.84 moles of water. That's how many moles of water are required. Now the reason why I was so insistent on doing mole conversions earlier in the year is because we need to be able to take units like grams to moles and then be able to take moles back to units. Now in this particular case, I'm not doing it in grams. This is a liquid. I'm not doing 22.4 liters. What it's asking for is how many molecules. So molecules are particles, numbers of particles. How do I do that? 2.84 moles of water. I want to have my number of particles over 1 mole. 6.02 times 10 to the 23rd molecules over 1 mole. My moles cancel out. I get 2.84 times 6.02, 17 point, we'll call that 17.1. 17.1. Now if I write 17.1 molecules, that's ridiculous. This is 6, basically 6 with 23 zeros after it. I'm multiplying it by almost 3. I can't expect to just get 17.1 molecules. You've got to think about what you're doing. Do not leave out that 10 to the 23rd molecules. Now this is 17.1 times 10 to the 23rd molecules, which is not in proper scientific notation. Scientific notation has to be a number between 1 and 9.9 repeating, basically 10. So 1.71 times 10 to the 24th molecules is the acceptable answer for molecules of water. Keep your units there. If I have those units and I ask myself, is that what I was supposed to find? Yes. Am I looking for molecules of water? Yes. Everything's good in that particular situation. All right, moving on to the next problem. Oh boy. A little bit of a tape issue. Technical difficulties here. So let me move this up. Almost there. Looks pretty darn good. I'll just move it over a teensy bit. All right, we're lined up. So we're talking about methane here. Methane is natural gas. It's one way we make energy. I want to make sure that you're aware of these things because we are a very energy dependent society. We have to get our energy from somewhere. Anytime we get energy, there are trade-offs. Notice this kind of energy, we're burning oxygen, we're producing carbon dioxide and water. Now I have to ask myself, is this balanced? I don't think it is properly balanced. I have one carbon, that's good. I have four hydrogens, that's good, but I have 1, 2, 3, 4, 5, 6 oxygen, so I actually need this to be a 3. And that's actually extremely important because, oh, actually it's not. It's asking how much energy should be produced. Oh, this is a thermochemistry problem. My mistake. Again, we burn this to get energy. Very important. Would I be able to calculate, if I did a stoichiometry problem, would I be able to calculate number of oxygen molecules I would need? Absolutely. Number of liters of oxygen gas at STP? Absolutely. I should be able to do that. Amount of carbon dioxide produced? Yes. Amount of water produced? Yes. This is an energy problem, okay? Heat of combustion. Change in heat. When this is burned, how much heat is released? Now in this particular case, the heat is released because it's a negative number, which means energy is coming out of this reaction. The actual equation, if I wrote it out, would be for 1 mole of methane and 3 moles of oxygen, I would produce 1 mole of carbon dioxide, I would produce 4 moles of water, and I would produce 802.2 kilojoules of energy. Why is it not a negative number? Because that minus is not talking about negative energy. Negative energy is something in physics. We don't talk about it in chemistry. This means it's coming out of the reaction. This energy, this 802 kilojoules, is stored in these chemical bonds. When this methane is burned, that energy is released. It comes out of the reaction as a product. Most of it is heat, although there could be some other possibilities of energy beyond heat. Like there's some light that comes out and there is some mechanical energy, movement energy that comes out. If this were a positive number, it would mean that the energy had to go into the reaction, and that energy is now stored by the reactants. But this is a negative energy, negative sign of energy, not negative energy. Please be careful about that. Negative sign for energy, meaning this is an exothermic reaction. It gives off heat. When we burn natural gas, we release energy. That's a lot of how we get our energy still nowadays. This is one of the fossil fuels, although this can be produced by other means. This can be produced by breaking down cow poop. This can be breaking down garbage. Some of the big landfills actually capture methane that bacteria are producing inside the landfill where oxygen can't reach. They're producing methane, and then some waste management companies are grabbing that methane and using it to get energy, which is not a bad idea. Now, it's saying how much energy should be released when 70 grams of methane are burned in an excess of oxygen. Again, the excess oxygen means we have more oxygen than we possibly need. We're not going to run out of oxygen. We have an atmosphere around us that's 21% oxygen approximately. We don't have to worry about running out of oxygen anytime soon. I have 70 grams of methane. Now, I'm going to turn that from grams into moles. Those are my steps. Balanced equation, units to moles. So, 70, my units cancel out. I have 70 divided by 16, 4.38 approximately moles of methane. All right, now, what do I do with that? It's saying how much energy should be released in this particular situation. What do I do with that? I treat my energy just like I would treat any other mole ratio. For 1 mole of this, I make 1 mole of that. For 1 mole of this, I make 4 moles of that. For 1 mole of this, I make 802.2 kilojoules of energy. So, how would I then set this up? Again, I can do it either one of two ways. 1 mole of methane over 802.2 kilojoules of energy equals 4.384, or 4.38 moles of methane over X, and my X will be the number of kilojoules of energy. So in that case, it would be X equals 4.38 times 802.2, which would equal 3,513, but keeping it to 3 sig figs would be 3,510 kilojoules. Or I could take my number at the top and 1 mole would be 802.2 kilojoules. So it'd be so my moles cancel out. 4.38 times 802.2, and surprise, surprise, it's 30,510 kilojoules. Now in stoichiometry, I would have to take those units and go back into moles. But energy is energy is energy. There's no, I have my units of energy already. So actually this thermochemistry problem is a little bit simpler. My answer, how much energy should be released, is 3,510 kilojoules of energy. And that is the end of page 2. I will stop and continue with page 3. See you soon.